Hello everyone, welcome back to my channel Cosmoki. In this lecture, I'll be discussing about another question from Dynamic Programming series, which is count sorted vowel strings. In this question, we are given an integer n and we have to return the number of strings of length n that consist only of vowels and are lexicographically sorted. Now, lexicographically sorted strings are those strings where the letter and its previous letter are following a pattern as similar in case of alphabetical order. What I mean is, consider this string here. In this string, you can see E always comes after A in the alphabetical order. Similarly, H always comes after E, and similarly, T always comes after H, but I comes before T. And here in this case, the order does not get followed, and that's why this string is not lexicographically sorted. While considering another string where S is A, E, H, T, Y, in this case you can see Y always comes after T, T always comes after H, and H always comes after E, similarly A also. And hence this is lexicographically sorted string. Now let's understand. In the question we have been asked to return all the possible combinations which are formed from these vowel characters. We only need to consider the vowel characters and we need to form all the possible combinations with only of length n and in the lexicographically sorted order. So, for understanding the question, I have taken an example where n is equals to 4. You can see here n is equals to 4. N is equals to 4 means that our string should be of length only 4. So for building all the lexicographically strings, we'll be taking the strings from letter A because we know that the lexicographically ordered form of these characters is always A, E, I, O, U. So we'll be always starting from A, and then at every position we'll have to only consider A. So this is the very first lexicographically ordered string. Similarly, we'll be start changing the character from the last to first, following the pattern from last to first, because we can easily see that if we manipulate, oh, sorry, if we manipulate here the last character and if we manipulating the character from the second one, because we know that we are starting from the first, we need to first consider all the combinations with starting from the letter A, and then only we can switch to another character, that is E. So if we'll be taking E here and then A here, you can see this string does not follow the lexicographical order because here E comes before A, and so we'll always be starting by modifying the characters from the last to first, and hence we are modifying here E and then I and then O and then U in the lexicographical order. Similarly, now you can see we have considered all the characters for the string where triple A is the starting point. Now we will be considering the third row. For that, as we know, we have already taken all the possibilities of A. So now we have to take the another possibility of another character, which is E. So here we have E. And here also we can't start from like this A, E, A, because another it is violating the principle of lexicographically sorted order. And hence we have already taken E only. And then I, O, U. Similarly, you can see, you can pause the video here and I would suggest you to try once all the possibilities for a single character so that you will get to know that how even in the at the back end of the program also how these strings will be generated. Although as soon as I'll be telling you the solution, the whole solution doesn't lie in generating these full strings, because this will lead to the solution of very huge complexity, which we always need to avoid. Because you can see, if we start building all the strings from scratch, like building the string this one, then this, so we need to follow backtracking approach, which might result to exponential complexities too. So we need to avoid that. As soon as you will build some of the strings, so you will be able to visualize a pattern, and that's why I'm suggesting you to build this whole strings by yourself so that you can get a pattern. Let me change the color. Okay, so the pattern here is, consider this pack of strings. Why do I have taken only these pack of strings? Because here we have modified the last character only, and that's why the number of strings where we have the last string only modified are 5. Now considering the another pack of strings where the third most character, second last characters are modified. In this case we have pack of 4. Similarly, you can see here we have pack of 3, and for here we have pack of 2, for here we have pack of 1. Now starting till now we have modified the third character. In this case we have starting modifying the second column, this one. So as we have taken all the possibilities of A character, now we will be switching to E. You can see here we have taken all the possibilities of E. And so here we got the pack of 4, then 3, then 2, then 1. Similarly, for I we got the pack of 3, 2, 1. For O we got the pack of 2 and 1. And for 2 is here and 1 is here. Yeah. And for U we got the pack of 1 only. So you can see there lie a beautiful pattern for A, E, I, O, U. For A, we got 4, 5, 4, 3, 2, 1. For I, we got 4, 3, 2, 1. For E, sorry. And for I, we got 3, 2, 1. For O, we got 2, 1. And for U, we got 1 only. So you can see that yes, there actually lies a pattern. And because we just need to return the count of the strings, then why do we need to generate all these strings and then counting and then returning? It will lead the solution of huge complexity. So to avoid such a solution, we'll be considering this pattern solution. Now, I would say that is another kind of observation. And this observation leads to another observation, which is, I would suggest you to calculate or build the strings from scratch, like by trying through dry run or by trying it yourself. You will get to know that for n is equals to 1, we are able to generate 1 string each here. Alright, for n is equals to 2, we are able to generate 5, 4, 3, 2, 1. For n is equals to 3, we are able to get 15, 10, 6, 3 and 1. And for n is equals to 4, 35, 20, 10, 4, 1. So basically there exists a pattern among these, and the pattern is, start seeing the pattern from the last character. Like here we have 1. For getting the another character for n is equals to 2, we can take the help of the previously generated numbers. Like by default for n is equals to 1, we all know the possibility will be only of 5. That means for each character we will be able to get only 1 string for each character. Alright, that's why this is always fixed. You can take it as a base case too for this question. If we start from U, you can say for n is equals to 2, we can easily find 1 plus 1 will give me 2. Similarly, 2 plus 1 will give me 3. 3 plus 1 will give me 4. and 4 plus 1 will give me 5. Similarly, for n is equals to for 3, we are able to generate all the possibility of counting from the n is equals to 2 itself. Like for 1, it is always fixed that we will be starting from 1 itself. So for n is equals to 3, first character is 1. Now start adding the previous character of the previous n. Like for 3, the previous n will be 2. So we'll be adding the previous character of 1. Like it's 2 plus 1, 3. 2 plus 1, 3. Then 3 plus 3, 6. 6 plus 4, 10. 10 plus 5, 15. Similarly, for n is equals to 4, 1 plus 3, 4. 4 plus 6, 10. 10 plus 10, 20, and 20 plus 15 is 35. So you can see that there lies a beautiful pattern which easily resolve our solution and the approach. We don't need to go to these tricky solutions of backtracking and all. We can easily solve this within big O of n time complexity using just single loop and having inner loop of just 5 iterations. Why I am saying 5 iterations? Because consider, let me explain you from the starting. What I am doing is I have considered a DP array which will be storing, not n here, this will be 5. I am considering a DP array of 5 size which will be storing all the possible combinations of each character for each length. Like for n is equals to 1, it's already fixed, we'll be having just 1, 1, 1. And for n is equals to 2, we can generate from the n is equals to 1. Like 2 plus 1, 3, 3 plus 1, 4, 4 plus 1, 5. So it's easily updated. Similarly, for n is equals to 3, we can generate from this array itself. 1 will be always fixed here. For n is for the uth character, 2 plus 1, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 15. Similarly, we can generate any number of such combinations for the furthermore value of n. So what we just need to do here, we just need to use only one loop starting from 2, because we have already fixed n is equals to 1 in our array. So we just need to take the single loop. We can easily update the value in the DP array. And for that we need 5 iterations of this DP array also. Alright, I would suggest you to start from the last because we are updating the values from the last one. So it will be always in this way. Now you can see dp add j minus 1 is equals to dp add j plus dp add j minus 1. This is what we are doing actually. We are just adding the previous element's value to the current value. Alright. And in such a way, we are able to get the possibility of combinations for each character. And so at the end, we can just run one single loop for calculating the sum of all these values in the DP array itself. Sum plus is equals to DP at I. And the sum will be our answer. And so how easy the solution has become, that we have reduced it from backtracking solution to just linear times complexity solution. You can see, as I have explained you now, I have done the same. I have initialized a vector and then the loop of n iterations, then the inner loop, and here I have calculated the sum and then returned in the same way. So if I run it, you can see the solution is alright. So I hope you would have understood my solution. Thanks for watching my video.